All right, it's time to begin. Welcome to the IFRR Global Colloquia, and this morning we're having Salah Sukaraya from the University of Sydney is going to be talking about robotics and agriculture. My name is Peter Cook, and I'm moderating the session today. I'm going to share a couple of slides here and just give you a little bit of background about agriculture, which is something human beings have been doing for well over 10,000 years. It's a very ancient human activity and, absolutely critical to our survival as a species. We absolutely need to have food. It's a massive imperative. And if we, put this in some sort of context, if we look at the number of human beings on the planet, we've got an awful lot of mouths to feed. And if we look at the way, this is some wonderful statistics I got from the FAO. You look at how we use land on our planet, 50% of the habitable land is now devoted to agriculture. And you can see how the fraction of land that we've used has grown massively certainly over the last few hundred years. Of that 50% of agriculture land, only 23% of it's used for cropping, yet it provides the bulk of our protein and our calories. 2/3 of our land is used for livestock production, which produces actually a very small portion of calories and protein. So it really says something about the sort of foods that we should be eating, because this is not sustainable to have more and more land devoted to agriculture. We need some efficiencies. And if we actually look at the amount of land required per person over a very long period of time, this is quite a fascinating plot. And it shows that in the last 100 years or so, the amount of land required per person has fallen dramatically. And the reasons for that really are the massive innovations that have happened in agriculture. And that's been huge boosts in genetics, from original sort of just ad hoc breeding of plant species through to more modern genetic engineering, mechanization, moving from animal power through steam power through increasingly large diesel-powered machines, which can cover a lot of land in a short amount of time, and of course to revolution in chemicals for controlling herb weeds and pests. So three massive revolutions really have enabled us to produce the amount of food that we can today. And I think the next revolution is going to be in automation and robotics, in addition to these revolutions that we've already had. So in this session today, it is interactive. And so members of the audience, if you'd like to ask a question, please go to this Slido site, log in with this particular code, and put your questions there. There'll be two opportunities to ask questions during this event. We have an eminent panel joining us this morning. So we have Jim Ostrowski. He's the Chief Technical Officer of Blue River Technology. So one of the bigger and perhaps oldest robotic agriculture companies. We have Professor Elizabeth Sklar from the University of Lincoln, and she's Research Director for their Center for Agri-Robotics. We have Brian Lowe from the National University of Singapore, and we have Chris McCool, an ex-colleague of mine. He's now a professor at University of Bonn and heads the Department of Agricultural Robotics and Engineering. And our speaker this morning is Salah Sukaraya. Salah is a professor of robotics and intelligent systems at the University of Sydney. He spent a time as an associate dean, and he spent time as the director of research and innovation at the Australian Centre for Field Robotics, which is probably one of the largest field robotics centres in the world. And now he's CEO of an ag tech startup company, and some of its activities is what he will talk to us about this morning. I've known Salah for a very long time. The robotics community in Australia is kind of small. Probably first met Salah when he was a PhD student working on outdoor robot navigation for container ports. And he's done a lot of amazing work in aerial vehicles, unmanned aerial vehicles, and in last decade at least, has been working very intensely in the agriculture area. So without any more from me, I'm going to hand it over to Salah to tell us about robots in agriculture.
Great, Peter, thank you. Thank you so much, it was great. And I assume you can all hear me well.
Yeah.
So I'm just going to share the screen and there we go. Okay.
We can see you.
Great. Good morning, everyone, or good afternoon, or good night, good evening, wherever you are in the world. Thank you to IFRR for the invitation. It's a great honour. It's great to be in front of all your peers and being able to talk about some of the work that has been going on, work that's not being done in isolation. Obviously, it's been a big team, and but also collectively with the rest of the community, being able to understand different elements of robotics, even in different industries, and how they may come into ag. Today is National Ag Day in Australia, so it's fortuitous, it's coincidental, whatever it might be, but it's a great to well, happy farmers. We've got lots of shirts now that say "I love farmers" now walking around, so everyone's going around to do that. But it's special. It's a special day. It's also been a great activity over the last decade working in this area, and it's been around a big team and lots of funding from different organisations. So without them, a lot of this work that I'm going to be presenting today wouldn't have been around. So we've had funding from different parts of the agriculture community and lots of PhD researchers as well as engineering team. So this was an image that I quite liked a while ago. I brought it up once when I was talking at an ag conference around farmers, and the question was whether this was the future of ag. And when this was 10, 12 years ago, and back then when they thought about ag robotics, it was kind of like humanoids and whatever might be walking around. But the picture also highlights something that I think is important when we look at field robotics and agriculture. So we're talking digital, we're talking mechatronics, but more importantly, we're talking about biophysical systems, and they change and they evolve, and they do so daily, and they do so during the day, whether it's at night or in the morning. And so because of that, it's quite a complex problem. And when you're dealing with building machinery that have to work outdoors 24 hours, 7 days a week, all weather condition, different soil types, etc., it becomes quite a complex but a fascinating area to work in. So whether that's the future of ag is, I don't know if it's, as Peter mentioned in his intro slides, it's always been the future of ag. This is a postcard. I think it was a Parisian newspaper, so it was from Paris in the year 1900 or 1901, and they asked Parisians what they thought the year 2000 would look like. And so the Parisians would come back and say, we think this, this, and that, and this is one of the postcards that was developed, right? And so it's always been in the in people's minds that agriculture, which was highly labor intensive and use of lots of land, would one day be easy, and so a farmer would be able to sit there, push some buttons, draw some levers, and then all of a sudden, things would move around and we'd grow and harvest. If you look at how that's changed over the years, this is, I'm going to show you another graph, and I know Pete's shown you some of them, but this one is interesting. It's a log graph. On the left there is the output per hectare. So on the y-axis, and on the x-axis is the output per worker. And as you start to see things stable off, what it's really telling you is we're reaching the limits. We're reaching the limits of both productivity of land, and we're reaching the limits when it comes to the productivity of the worker. And this may not be the case in all places, and I'll talk a little bit about developing countries and the role that robotics and AI might have in developing countries. But otherwise, it's an interesting story. And if you kind of look at another image that that you grab, this is from Case, their autonomous tractor. If I hark back to that humanoid robot that I showed you before, and now this, which is kind of showing you or indicating what it looks like. And there's a few things in this picture as well. So autonomy, so it's just a tractor, I guess, with GPS and maybe some lasers, some detection systems on board for collision avoidance. But the thing that it tows would be highly precise. That would either be doing precision spraying or precision weeding or precision seeding, down to the centimeter level. But the uniformity of the crop that is in the background is important too. So what we're seeing when we look at reduction in labour productivity is the desire to go into more mechanisation and robotics, hence automation, as you see in this picture. As Pete mentioned before, a lot of work in genetics, but that's also because of the fact that there's been a reduction in land productivity. And so what you get is a lot more uniformity of crops, but a lot more monocultures that exist. So farmers are getting used to growing a certain type of crop over and over again. So they're getting more structure in the land. And that makes automation easy, but it may not necessarily be a good thing when it comes to nutrition and things like that. So there's all these reasons as to why being able to look at different types of crops growing, and hence using smaller robots might be something of interest. There are other factors that come into play, and I'll jump through these ones quite quickly. The farmer is getting older. This is just showing in Australia that the average age of the farmer is somewhere between 55 and 65. Kids don't want to work on the land. They're going into the city, especially in developed countries where it's a lot more about services and cities. So they're getting older. We're getting a lot more consolidation of farms. So smaller farms are disappearing. If you look at labour in ag, at least in Australia, it's diminishing over and over again. So it's harder to find people who want to work on farm, let alone keeping it within the family. And in Australia anyway, when you look at the labour cost, we have one of the highest minimum wages in the world. And this fluctuates for somewhere between 1 and 3 all the time every year. So all these factors come together and have an impact on what happens on farm. If I look at it from an engineering perspective, there are a few things here. This is kind of showing you a systems diagram of what happens on farm. And it's looking at how you would model farm activity and then apply optimization techniques on top of it. But on the left there, you'll see, on the far left, you'll see aspects around pests and diseases. In the middle there, around what happens between the soil and the plant. And on the right there, some external effects that might be happening on the plant. And so people now are trying to look at how you might model whole of farm systems, how you might then throw optimization algorithms across it, as well as large scale big data fusion algorithms, and try and look at optimizing the system along with the robotics and mechanization. This is a systems diagram of the labor force, and this is not just something in Australia, but around the world. It's a complex thing. This, the farmers dealing with seasonal workers, people who come in and out, casual workers. Sometimes they come, sometimes they don't. Sometimes the farmer next door offers them $1 an hour more and they'll go there instead. And so there's many complex factors in here, and immigration also kicks in, which is an important topic recently in many parts of the world. And on the right there, if you look at what's happening, the farmer sits in the top left-hand corner under production, and we sit in the bottom right-hand corner under dining and eating and whatever it might be. And we want the highest quality food coming to us at the cheapest price. And yet there's all this activity that happens between the farmer and us. And so what ends up happening is the farmer ends up getting driven to deliver quality products at a lower cost over and over again. And hence another reason as to why mechanization, robotics is kicking in. So they're all the factors that kick in. And as Pete mentioned, he showed you the graph there of people. I don't know whether it's 9 billion people now or 10 billion people, but it's the projection that about, the growing population, we need to feed more people. We can't use more land because we're already depleting a lot of the nutrients in the soil. So the question then comes around precision agriculture when it comes to robotics and intelligent systems. So that's a bit about the background. I just wanted to hopefully give a perspective of why we're doing all this and how it kicks in. The journey for us started back in probably just before 1999, somewhere about 97. I want to kind of show you some drone work because it leads into why we moved in into the ground robotics work. So we had this program that ran for a number of years that was looking at building flight platforms from scratch. You couldn't buy these things off the shelf, and then flying them cooperatively and collecting large amounts of data. And what I wanted to highlight here was you had to build your own system, everything from the platform, the nav system, the sensing, the flight control, everything from scratch. And it cost us about $750,000 per platform to build each one of these. Back then, you could build some high-res data, about 1 meter, 2 meters. It was just black and white visual data. We process it offline, come back the next day, and we get this terrain map that came out. And then at about 2003, 2004, we started to notice that there was a growing interest in the civilian area around UAVs and drones. So a lot of this work was done in the aerospace sector. And we wanted to look at what were the key elements that, in Australia anyway, where drones could be used. And one of those key elements was around weeds. So invasive pests that would come along and not do two things: ruin your land in terms of the soil, but also suck out the nutrients and hence stop your crops from growing properly. And in Australia, it's close to $4 billion a year of lost agriculture because of weeds. So that kind of triggered us, and then we kind of started looking for some funding and started going out there and start putting some drones together. And at that time, there were a lot of startups that were forming that were building things from either drones, but more importantly, autopilot systems. So a lot of autopilot systems being formed in that time space around 2005, 2006, which meant the platform cost started to decrease. So we had about, you could buy a platform for 50K and autopilots around 30K. The image on the yellow platform that you see there is just an off-the-shelf hobby remote control aircraft. We put, at the time it was cloud cap autopilot units internally. And then you put this vision system on board and off you went from there. And we had PC 104s, for those that remember that. And you could then fly around large areas and start to collect a lot of data. In the bottom left-hand corner, again, in a remote control helicopter, about a 2-meter rotor. And then what we did was we added our own sensor payload box, PC 104 in there with camera, and again, do a whole bunch of things around aquatic weed detection. So that was the cost of the platforms. And at the time, SVMs were starting to kick in, for those who remember support vector machines. And that was kind of helping us a lot with doing some machine learning elements. So we take these cameras and we'd start collecting data, and then we could start classifying individual features. And we were starting to get into the whole Gaussian process as well. So we started with some SVMs and we could detect weeds, and then we moved into Gaussian processes. It was happening around 2008, 2010, and you could classify individual plants. You could say this was a tree, native tree, but this particular tree was a weed. That activity kept growing, and then probably more lately, around 2016, we had a large scale fund looking at satellite data, low altitude drones and high altitude drones, and how you would fuse information together. Now, the whole platform solution was less than 50K. We didn't have to do any autopilot work. We didn't have to do any platforms. The things would just start, put your GPS coordinates, and off you went from there. But you could now also look at some cloud-based architecture, and from that cloud-based architecture, you could then start looking at GPs in anger, and we looked at them quite extensively. And what we could start to do was this multi-level fusion. So you could take the satellite data, which was at about a 5-meter hyperspectral set, and you could take low altitude and mid-altitude aircraft data, which was anywhere between a couple of centimeters up to a meter. And you could learn and classify weeds in the low altitude data, and then using GPs, infer based on the hyperspectral satellite data where you think the weeds might be in other parts of the area. So in this case here, where it might be a 10 by 10 kilometer area, we were actually inferring where weeds could be that the drones would then go. So you're starting to couple in the machine learning along with the decision-making process so that you weren't flying around continuously. What I wanted to show with that drone work was the initial cost and the activity, and how that started to diminish with time as you went through, as well as the capability of the algorithms and how that started to get better and better. And when we started to do all this work, we were engaging a lot with farmers, and the farmers were really loving the fact that we could detect weeds, but it wasn't enough for them. And really, if you asked farmers what they were looking for, they wanted something like this. They wanted that, okay, it's great that you could detect all these drones, but can you then kind of land on the ground and spray the weeds or something like that? So a drone on wheels is really what they were looking for. And it started to get us to think a little bit more about what activity they do on farm other than weeding, because again, we were going to go back to the beginning again, right? Which was high cost platforms. You had to bespoke solutions that you had to work with the farmer and then and go from there. So we started to work with the growers, and we started to introduce a lot of work that we did in mining and in aerospace, not just in terms of the mechatronics, but also in terms of the thinking about how we would apply that. So the first kind of activity was around tree crops, and we're looking at data analytics solutions here, trying to look at how ground robots could help improve knowledge and certainty about what was happening on farm. And I'm going to walk you through this a little bit, just so that you, and not through the boxes, just a quick look and you can kind of see what happens. But it's really kind of showing you the thinking process that a farmer might go through from the beginning all the way through to harvesting. and they have to look at everything such as, I look at the tree structure. What does the tree structure look like? Do I want to get rid of some of these branches because I don't want too many branches, so I'll suck up too many nutrients. Remember that if in that previous graph where I showed you where they're doing the production and we're sitting right here at the end and we're eating, in Australia at least, supermarkets will come along and say, you know, this apple here has to be 50 millimeters and it can't be 47 and it can't be 53. So a farmer who's 6 months planning, right? So from now planning out 6 months is saying, how do I get this apple to be within plus or minus a couple of millimeters by the end of it all, given all the weather conditions, soil conditions, et cetera, that keep changing as we go through. So they go through this thinking process. Are there too many branches? Not enough branches. Too many flowers? Not enough flowers. Do I get rid of flowers? Do I look at the fruit buds? How many of those do I get rid of, et cetera? And they're constantly optimizing as they go through. And if you're talking about a 100-hectare farm, somehow they have to translate that innate knowledge that they've learned down to 100 different workers. And they have to tell these workers, now go out there and if you see 3 flowers on this branch, I want you to take out 2. And if you see whatever it might be, right? So you've got to go through that. But from a robotics perspective, if you look at that and start to ask yourself, actually, what does the information and decision flow look like from a farmer's perspective? So we're looking at time here, going clockwise, from pre-pruning all the way through across. You'll see that there's a lot of different elements that happen in each one of those, and I've kind of highlighted these things through the text. And the brackets at the end are the important parts, because that's what told us what we should be looking at when it comes to the robotic solutions. The brackets are really telling you the first variable in that bracket is how much information they have. And the second variable they're telling you is what impact that has on the farming production process. So for example, in the top left-hand corner where it says quality, maybe I was here, quality, size, defects, maturity, color, they have low information about that, but it has a high impact on their decision process. So if you started to look at it from a robotics perspective, the low-hanging fruit, and pardon the pun, but the low-hanging fruit is to go along and go to a farmer, wherever there's low information, but it has a high impact on your decision-making, I can introduce robotics in there because I know it will have a high impact on what you need to do. Okay, and hopefully, even though the cost of introducing the technology may be high, you can start to introduce it because you know that it has a high impact and potentially high return for the farmer. So the dark elements there, counting fruitlets, looking at quality and size, yield estimate, being able to do a count on flower numbers, how many flowers are that need to be removed, all those things are quite important for a farmer. So we then embarked on developing solutions for that. And this was the first platform, which was just an off-the-shelf 4-wheel Segway, a bit of a Frankenstein of a robot where we just built the sensor tree, put a whole bunch of different sensors on it, everything that we could possibly imagine, because we had no idea. This was back in 2000 and maybe 11. No idea what sensors would work, what data would come back, and being able to look at everything from trees. But what you'll notice is there's information about what happens on the tree. And also we had a natural gamma sensor, which could measure ions in the soil, and also a soil conductivity sensor, which would measure the water conductivity. So what we were trying to do was go, what was happening below the ground and what was happening above the ground? And can we start to build correlations between that type of information, because and start to do that? And this is obvious to everyone around here. You know, you obviously get different types of spectral information, different types of images. For us, we can see a tree continuously, but what we keep telling the farmers is, you know, when a farmer looks at this, says, oh yeah, I can see the trees. Why can't the robot see the tree? You know, trying to tell them about, you know, how the robot has to learn and undertake machine learning. Can you find correlations between different sensor qualities? All of those things become important. And we went through, you know, your classic, you know, SLAM techniques, transform techniques, your classic computer vision algorithms, and try to look at things as, can you detect, you know, in this particular case, what you're seeing is a collection of apple trees, and the apple trees have been cut in a way where they're in a 2D horizontal plane. So they're not your classic 3D kind of shaped apple trees. And so when you're going along, they practically look like a wall of apples. But in order to do precision ag, you've got to be able to segment out each apple tree. So looking at different techniques to be able to do that. And I'll talk a little bit about why that tree architecture becomes important when it comes to robotics later. This is in an almond plantation. Sorry, I'm just trying to see whether that works. Is that an image? It's just an image, sorry. Here it is here. So this is just the robot going through in an almond plantation using laser data and visual data to be able to segment out individual trees. So the robot's now going in real time saying tree, 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 using laser and using algorithms to kind of segment them out. It's also collecting the visual data, so it's able to extract out the visual information about each individual tree. And then once you've done that, obviously we've trained some models, and those models will come along and do things like count how many flowers there are, or count how many almonds there are on each individual tree. And then you start to deliver yield estimates for the farmer. So this look at all the almonds and then being able to do a yield estimate for the farmer. Now you can't penetrate into the tree using just laser and vision, obviously. So you do a lot of agronomic work where you're saying for this particular type of almond tree, because there might be different types of almond tree, we might go down a row and harvest all the almonds and count how many almonds was down that row for that particular type of tree. And then looking at the laser and visual data, we try and generate a correlation. So the laser data is building up a volume estimate of the tree. We're counting how many almonds there are that we can see. And based on the harvest, we work out a correlation. And from that, we can then start getting yield estimates for every single tree from there. So that becomes an element of yield estimation. This is just showing you some work that we then looked at. If you can detect individual plants then or trees, can you then come, so this, as you can see, it's just firing away at each individual apple. That's it in real time, and that's it in slow motion. And we did this, and we also looked at what it would do to kind of spray powder. So we were looking at the future of maybe pollination and what it would look like to practice back in auto-targeted pollination activities. So being able to look at individual flowers and then pollinating each individual flower. Now this was purely a bit of robotics fun. We had no idea whether this was useful in a farming context. It was just us, thinking, oh, that'd be cool to be able to do something like that. And we took it out, we put it on one of the bots. So you'll see there that little box, white box on the side there. It's got the camera system, but it's also got a little spray unit. And what it's doing now is as the robot's going up and down the rows, it's detecting apples in this case in real time. Sorry, a bit of a lag. It's detecting apples in real time. And based on detecting apples, you can see it there firing out. It's about 30 frames a set, 30 hertz is what it's firing at. So it's just detecting and spraying individual apples and just firing away. This was just, as I mentioned before, it's just a couple of research students and some engineers, and we kind of thought this would be cool to do, but we had no idea. But once we showed the farmers were, it was very interesting because, and this touches on this co-creation activity that happens between the robotics group and the farming group. And remembering farmers are quite practical. They build their own systems on farm. They need to adapt. And so being able to sit down and do this co-creation becomes quite interesting. And from their perspective, when they saw this, it was like targeted pollination, being able to target individual fruit if you want to slow the fruit growth or even remove individual flowers. So for example, thinning becomes another element of interest to the farmers. There's still a bit of work to go. You can imagine you're trying to shoot at targets that might be a center or two centimeters at about 200 millimeters away, and you're moving at maybe 3 to 6 kilometers per hour, and there's lots of undulation in the terrain. So there's a lot of things that kick in that you have to make that work, but it's where you can see some of the future going. We also looked at harvesting, like many people are. This is one of our first attempt at soft gripper works, and just absolute coordinates, just being able to sit down and say, I know where the apples are in this case, can I go through there? And the original work around planning techniques and being able to harvest fruit, that led into work around how can you detect fruit when you've got occlusion, so when leaves are covering fruit, which is always going to be the case, and using information metrics in this case here. This would never work in real time on a farm. So it's just us looking at here. This was a Gaussian process implicit surface algorithms along with prior. So being able to use Gaussian process to predict what you think the shape of the object is, even when there's occlusion, given that you have a prior, which is, I know what apples look like. And then linking that into an information decision algorithm that then comes along and says, what angle should I look at next in order to get a better information set based on that. So that was some of the prior work to try and look at what occlusion might, how we might deal with occlusion. One of the important elements, and we touched on it a little bit here, but not enough. So this is visual surveying techniques. and just being able to look at harvesting, in this case here, lemons. Very easy concepts, as you can imagine, right? Because it's a nice yellow thing. That's a magnetic piece, right? So we stuck these things with magnets at the end of it all, just to make it a little bit easier. But it's one of those things where you're looking at and saying to yourself, what are all the different techniques that we can look at to try and look at harvesting? And recently we just went out and did a trial, and we took out the robotic arm, and we wanted to look at soft gripper work, because we had some soft gripper activity here. So we just popped this robotic arm with a bunch of generators on them and compressors, because we were looking at some soft gripper work, and then starting to look at, this was in a plum orchard, and looking at different soft grippers. And this is a classic failed attempt. So this is not going to go into the JFR paper, or the FR paper, or whatever we're going to call it. Right? So this is one of those classic fails, right? Where you try and harvest a bit of fruit, and looking at the soft gripper activity, and trying to see what works and what doesn't work in an external location, right? So I'll just jump through and kind of show, which for a real sense, along with the soft gripper, and being able to target that in different forms, right? And it was, so this is a fail when it comes to harvesting the fruit. It's a success when it comes to not damaging the branches. And that's one of the key things here about damage around branches. And things like that. And I wanted to just stop here for a second, because this is what I was mentioning before about a wall of fruit, as opposed to what you saw with the almonds or your classic style of tree architecture. The reason why this is important is because the future of automation, especially in quite complex areas like this, is not going to be about building different robots and throwing them onto farms, regardless of what the architecture of the farm would look like. What we're really seeing now is how roboticists and geneticists and also the farmers talk to each other about new types of architecture of plants, whether they're trees or vegetables or whatever it might be, to facilitate automation. Now, this particular grower here contacted me about 5 years ago and said, I want to harvest. And I said, there's no way you're harvesting, because you've got 3D vases and whatever it might be, shaped architecture. It's going to cost you $10 million of R&D funding, whatever it might be. What do I need to do? Well, you need to make it easy. If you can build like what the Apple industry does, build a trellis architecture, then that makes it easier. 5 years later, he's got 30 hectares of these plants growing. But without the automation, he's also reduced the labor cost element, because it's made it easier for everyone to be able to harvest. So that's kind of the backdrop around where we're going now with tree crops. How do you identify, sense individual fruit, individual flowers? How can you use then targeted spraying, harvesting tools to then come along and be able to manipulate the tree crop, even now down to pruning and thinning. There's a lot of work going on around the world in that space as well. So I'm going to stop there. That's the first part of the presentation, and before I head off into the second part, but opening it up to questions if there are any questions.
All right, thank you very much, Salah. And for those who tuned in, this is part one, and part two will come up shortly. It's my pleasure to introduce our special guest panelist, Vijay Kumar from University of Pennsylvania, who's joining us as well. So, panel, do you have any questions for Salah? Vijay.
Hey, great talk so far, Salah. I'd forgotten all about PC104 stacks and cloud cap autopilots. This is great. Hey, I just wanted to I mean, the magnitude of the problem you're addressing is just incredible. But at some level, you're looking at sort of measures like volumetric measures or hyperspectral measures, and try to correlate this at scale with things like number of almond on a tree. And I'm just wondering how you do it across trees, across farms, in a way that's compelling and convincing to the growers, because ultimately they have to conduct your experiments for you in order for all of this to work.
Yeah, it's a good question. And you can't so far you can't come along and develop, or our experience anyway, that you can't come along and develop a set of tools that will work across different types of trees or different types of vegetables, for example, or different types of broadacre crops. There are always going to be some modifications to that. So the way we targeted it was identifying which were the high value crops. So the slide that I showed you around information decision making that a farmer would have, and coupling that with what are the high value crops and the high cost crops. And so if you choose something like plums or nectarines or peaches, they're high value crops. They're and they're high cost crops because of the amount of effort that goes into everything from pruning to harvesting. And so they offer the best possible return for a farmer when they want to look at sensing and robotics. And they're the ones that we would tackle first. And yes, you start to build solutions that specifically cater for that type of commodity, that type of crop. And then if you came along and said, I wanted to go into citrus oranges, juice oranges, which is orange amongst green, they don't really care if it falls on the ground because they're just going to juice it all. You probably wouldn't approach that straight away because it's not a high value crop and it's not a high cost crop. It's probably something where as the technology matures and gets better and it becomes easier to process the data online, or whether it's the tools that you use, they'll probably be the second or third tier generation of growers that will start to see robotics come through.
Thank you.
Do you have any other questions from the panelists?
Yeah, so
Elizabeth.
yes, thank you. So Salah, thank you for the first part of your talk. Really, really interesting to see everything that you're doing. One of the things that I noticed is that you're moving from one kind of crop to another. So from a technical standpoint, in terms of like transfer learning kinds of technologies, are you able to use some of the algorithms that you developed, say in almonds, when you move to apples?
Yeah, no, it's at the moment now in tree crops, it's much harder. In vegetables, we've been able to kind of get some preliminary results around that. And again, it's one of those things where we've had to segment that out bit by bit. So for example, lettuce of a certain variety across different soil types in different conditions, can we use transfer learning techniques to kind of pass through that? And the answer to that is a yes, and it's getting better. Different genetics of lettuce, so different types of lettuce, require a bit more work. In some cases, we can apply transfer learning. In a lot of the cases, we've got to relearn the whole model process again. And jumping from, say, lettuce to cauliflower, or lettuce to, or it's harder, but broccoli to cauliflower is a little bit easier. And so you start to see these little traits that you can start to apply transfer learning techniques to in that form. So the answer is yes, but it's early stages at the moment now for us.
Okay, thank you.
Brian here. Hi.
Yeah, hey, Brian.
Hi. Really nice work on the use of especially the Gaussian process that I've seen throughout your slides. So I'm wondering, could you give us more information about how you are, why are you using Gaussian process as opposed to deep learning that's often being used, and any advice for people doing or researchers working on Gaussian process modeling going forward so that it could help you out?
Yes, so what you would have seen is the history of it. So we went from computer vision techniques to support vector machines to Gaussian processes, now to deep learning. So the work that you see, all the fruit detection, flower detection work now is using deep learning techniques, the classic deep learning techniques. So we are using all of that now.
Right.
And we have it, the Gaussian process initially was because I think it was just it was a phase in the community, and we liked all the maths and the algorithms that was going through, and we kind of started to use all that. But as the deep learning algorithms got better, we moved across into that, especially obviously fundamentally what it came down to is when we started wanting to do real-time manipulation, whatever that might be, or real-time implementation on a farm, being able to just learn a model that can work within a specific condition set and run that in real time became important.
Right, okay.
We've got a few questions coming in from the audience. I'm going to hold those over until after Salah's part two. Jim, you had a question, and then we'll move on to part two.
Sure, real quick. Yeah, first, thanks, Salah. This is fantastic. Been a great talk so far. I'm just curious, with a lot of this work, there's some complex manipulations that are required. You've got a fairly sophisticated robotic arm. And one of the things I've seen is it's been pretty hard for companies to bridge that gap of going from more research into production where it requires these complex manipulations. What's your kind of take on that in terms of how do we bridge that gap? How do we move from kind of lab or kind of one-offs to something that can be really put into production?
Yeah, it's a good question. I think the robotic tools that I showed here, which were harvesting, for example, they're not going to be the end solution for any commercial implementation. So they're good for R&D work and being able to do that. But you're right. There's a lot of there are some startups out there now that are looking at harvesting using much more Cartesian-based manipulation techniques, and I think that's more likely the approach to take. But I think, to answer your question more directly, what I don't believe is going to happen is we're going to have this ubiquitous set of robotic arms that can work on different plantations or anything, or different tree crop scenarios. We have to talk to the farmers, and we have to be able to architect the farm in a way that allows the introduction of those robotic arms, whatever form they might be, to come in. You have to simplify the robotic arm. We're talking about repetitive motions that have to happen 1 million times a day in dusty environments, et cetera, so that the arm has to be a lot simpler than what it is now. Potentially removing some of the effects about daytime operations by operating at night, although a farmer generally doesn't like that because they need the flexibility to do that, but that could be another solution. But then I think the architecting of the tree is important, and it's important because a farmer doesn't mind losing 1/3 of their yield because they've had to re-architect the trees if it means increasing their profit overall because they've reduced the labor cost. And so it's about having that discussion and bring that together. But I think we're still a while away from learning about what is the right thing, but generally I think the principles are reduce the complexity of the arm, maybe operate at night, architect the trees.
Okay, thanks very much for those answers and discussion. As I said, keep the questions coming in on Slido, and we will get to those after Salah's part 2. And Salah, back to you.
Okay, into row crops, same principle and process that we saw before. This is the same type of discussion process, but they're now looking at lettuce, for example. And what does a farmer go through lettuce? And I could, go through the same process and start speaking at each individual point and saying to a farmer, how much knowledge do you have about this? How much impact does it have in your particular location? For your production. Highlight those points and start to introduce robotics from there. So we were in an interesting position because we were working on the tree crops, and the vegetable industry got jealous. And this is one of those classic, it's really nice, right? Because the vegetable industry got jealous and said, okay, we want robots on vegetable farms. And what do you need to do to kind of get that going? So we started looking at, do we take a tractor and start to automate a tractor? Are there other solutions out there that we could look at? But they gave us enough funding for us to rethink aspects around robotics on farm. This was probably 2014 at the time, and this was Ladybird. And there was a few things obviously that were happening. Solar energy was getting a lot more efficient and cheaper. We could see that trend. Batteries were doing the same thing, so that was great. And then we started, okay, we'll go solar electric. Let's go to a vegetable farm. Okay, go to another vegetable farm. Okay, sorry, they've got different rows, different heights. We'll go to a third one, different rows, different heights. So you started to look at all these different problems that you had within the vegetable farm. So we built Ladybird in a way that allowed us to change the configuration, so for different height crops, by keeping the solar energy there, but the wings going up and down. For different row widths, we could then come along and adjust the wheels, and we could do all this on farm. And for then different height crops, you could then come along and adjust the sensor panel as well as the robotic arm manipulation panel. So that became an important tool, which then allowed us to go from farm to farm and start to, this thing could fit in the back of a trailer. You could go to one farm, roll it out, readjust it, and then you could go from there and start to apply the same techniques that we looked at with the tree crops, but in the vegetable industry. And the picture on the top right is just showing you the different sensors again, same process as before. Put all these sensors on board, start to learn what data works and what data comes back that actually works and tells us a lot more about the scenario in front of us. We built it as an omnidirectional robot because it was because the headland, which is this brown bit, was for different size farms. So sometimes they could be really small, and so you had to navigate and work your way around. So some control techniques there around omnidirectional drive. As you're going up and down the rows, can you measure slip on each individual wheel? Because you can easily get bogged on these, and start to look at different scenarios around there. We played a bit more agronomy in this particular project. So we did a lot more individual testing. So this is showing you an experiment on the university farm where we actually planted all this lettuce and we increased fertilizer down certain rows, decreased fertilizer, etc., increased water, decreased water. So we kind of did this controlled experiment. And then we could have Ladybird go up and down the rows, collecting all this information, laser hyperspectral vision. And we had a whole bunch of people run behind it and then start to collect leaves. And then you would go and process those that later. And the whole idea was to come along and start to understand, could you measure things such as health and biomass and quality of crops based on the information? So we're trying to up the value now of the information that was coming through from the robot. So this is just showing you from the looking down from Ladybird. So that was just the color checker. In this case, here's some chickpeas, and we're looking at detecting weeds and different types of plants and broccoli and whatever it might be. So there's a whole bunch of, and this is now using, going back to Brian's question, just using deep learning techniques and just applying that in this context. What's interesting is that we learned a whole bunch of things, right? So this is just a hyperspectral plot of the plants under those different controlled conditions, right? But along the left there's all these acronyms, and those acronyms represent different metrics that agronomists use to measure the performance of vegetable crops. Now, really cool. But what we found was that actually if you applied machine learning techniques, and again, different types of techniques, but if you applied machine learning techniques, you actually found that you could find correlations between spectral bands that none of the agronomy guys were using at that time. And that became an interesting process. So people were used to color cameras, they were used to infrared, so they could start to build up these different metrics on the left, so NDVI, NDVIR, whatever it might be, etc. But if you use machine learning techniques, you could actually start to find correlations between spectral bands that will give you a new metric that identified something such as potentially the plant was going to go into stress because of water, right? Or there was a certain inference that a certain pest was attacking the plant. You couldn't see the pest, but you could infer by the stress that the plant was going through because of the spectral responses that were coming back. So it became an interesting topic area that we could then come along and start to compare. And it was quite interesting because you had the machine learning guys now working with the agronomists, and that becomes a key element in this area. I mean, from before when I was talking about biophysical systems, to try and learn the qualities about what was happening with the plant based on the ag science that was coming through. And then we could do things like build up prediction models about what we thought the weight of the crop would be based on what we were inferring, and then measuring that crop as well. And the lettuce is hard, right? Because you've got a volume, but it's mainly water, right? And so you're trying to now infer the weight of this object that's mainly full of water by understanding stress and so forth, and then looking at and then harvesting that and measuring it and start to build up some correlation models from there. And we got some, the linear trend here is just showing you it's got some good correlation results. But where that led us into was, can you predict many weeks ahead of time what was going to happen to the plant? Because if you could, then could you use the robotics and the sensing to then change or adjust crop variability? So there's two things that a farmer wants. They want to get grade A crops, which means that they've met the supermarket's condition about a lettuce being 80 millimeters wide or whatever it might be. And also they want to minimize crop variability. So they want to have 100% of their crops as grade A. They don't want 70% of grade A and the other one's grade B and whatever, because they they get less money for those. So if you can predict ahead of time what's going to happen to each individual plant, can you adjust the behavior of those plants as you move through? So this goes back into some ag science, and you start to look at growth of a plant. So growth of the plant follows a nice sigmoid function as you go through. And then we went through the process of doing the same analysis as I showed you before, applying machine learning techniques and trying to use that to infer the growth of the plant ahead of time. All right, and that became an interesting area to work with. And we did repeated results after results. This is an iceberg lettuce, which is one of the most common lettuce, I don't know what it is, common lettuces in the world. And then it was interesting because the black line representing the different growth rates for different plants, the red line representing what we're estimating and the future results. So there's probably a Gaussian model predicting the future result in there. And what you notice is that if you it's a classic thing. If you observe only infrequently right at the beginning and try to predict forward, you get a large error. And what we found for lettuce anyway, in an 8 to 12 week production cycle, if you can get observations in the first 5 to 6 weeks, you get a very accurate estimate of what the rest of it's going to go through, because that's sigmoid function growth. You get a much better estimate of what's going to happen at the end of it all. And so that became a mechanism by which now we could come along and start to use these to predict ahead of time what we thought the plant was going to look like, each individual plant, and whether from there we could adjust it by saying more fertilizer, less fertilizer, but on an individual plant, not on a row or on a paddock or anything like that. Again, it's probably a few more years away before farmers would look at this and start to adopt this properly, but it's heading down that path about precision agriculture and how you would start to add them. So that was all on Ladybird, and we got a lot of interest from that to then build a prototype that worked on farm with all those solutions, and Ripper came along. Ripper now had a 24-hour capability. It could run for about 12 to 15 hours on batteries alone, and on a nice sunny day, you'd get the 24-hour capability coming through in there. It had to do a couple of things. One was the decision, so format's gone a bit off here, so decision support as well as crop interaction. And so it's the classic cycle, but running on a robot now. So it's from sensing, correction of information, using machine learning techniques to identify individual plants as well as individual weeds, then being able to look at control techniques to then everything from, you're moving it somewhere between 6 to 10 kilometers per hour. You're seeing all these things running past you very, very quickly. What do you do next? And so, looking at optimization techniques and control techniques to be able to understand what actually should be doing. So this is just a bot on a lettuce farm. It's running up and down the rows. It's now using real-time machine learning techniques, detecting individual plants, and we can assess the yield of each individual plant and starting to get to the point of assessing health quality of each individual plant as we're running through. So next you'll start to see some spheroid estimation techniques to try and estimate yield for the plant, as I mentioned before, because we could start to do that based on the research. If you can detect the weed, if you detect the plant, you can detect the weed, and then you can start looking at mechanical techniques. So how do we reduce chemical herbicides to be able to remove the amount of chemicals that are used on farms, scratching weeds? This is one of the benefits of automation, where repeatedly going out on a farm means you can tackle the weeds smaller, which makes it easier. And this is the targeted spraying techniques, where we're identifying each individual plant and then targeting each individual plant and spraying that each individual plant with whatever amount of chemicals that we think is necessary. And if you go back to the tree crop work, this is what we're doing here again, is water monitoring. So now we've got this capability of going, detecting information, acting on the plant, and then also doing subsoil information. So just for a quick break here on this element here, what this really means is that we're starting to build an agronomist that runs around digitally 24 hours, 7 days a week on farm, down to the individual plant. So an agronomist is that person who comes to the farmer and says, I looked at your farm, now this is what you should do for your whole farm. Usually the agronomist might take a sample set of 4 to 6 places around on a farm. And then so there's a broad decision that goes onto the paddock. But now what we're doing is we're taking that knowledge and digitizing it so that it comes down to the individual plant level. And that completely transforms the way operations work on farm and what a farmer needs to do. There's, just for the mechanics out there, there's lots of work that needs to be done around how you build these small robots in very undulating terrain. You're basically building almost like this, it's a drone in the sense that everything has to be precisely aligned. The sensors, the gimbals, the cameras, the computing system, everything on the frame, so that you've got a nice measurement source, but you're dealing with a terrain that's quite undulating, and you can't come along and build a very stiff robot doing that, because then you get the stiff rubber with wheels lifting up in the air. So how do you build the flexibility in the robot to deal with certain terrain is important. And the other thing is we did a little bit of modeling, airflow modeling work. This harkens back to my Formula One desires of being a Formula One driver, but we did some airflow modeling work around the ag bot and trying to look at how airflow works, because what we noticed was that depending on how you build the bot, you're going to start to get some high pressure and low pressure systems. And if you're starting to spray underneath the bot, then you've got to deal with and understand how these airflows work, because you're targeting something from 30 centimeters away, and you need to be able to get that right. So there was a lot of work around there in that space in the row crops, and we got to a point there where a farmer could come along now, click on any individual plant and see the history of the plant, as well as what the future prediction growth of that individual plant would look like. And then there was another level of optimization algorithms which would dictate where the robot would go next in order to reduce crop variability in terms of its actions, so that it didn't have to go up and down every single row. The same thing happened if we stick with these ground bots I'm going to switch now gear away from vegetables into grazing livestock, which is dealing with animals. Again, the same process. They have to worry about a whole bunch of things and what happens in the soil. At this particular point in time, the value for the farmer is the animal itself, so the beef or so the cattle, the sheep, the cow, whatever it might be. But understanding soil, understanding pasture is important in order to deal with a healthy animal. So there was many things we dealt with around designing robotic platforms for that. In this particular case, we built a bot called SwagBot. I know in the US, swag means something. In Australia, swag is a little bag that you carry at the end of a stick. And a swag man was a person who used to go from farm to farm and help a farmer, and they'd have this little swag at the back of a stick. So this was SwagBot, right? It didn't mean it had a swagger or anything like that, although it did eventually in its design. But it's an omnidirectional bot with a swivel point in the middle. It meant that we could come along and deal with quite complex and undulating terrain, which is what you'd find in a grazing livestock scenario. And we wanted to do the classic thing. The first thing that we ever wanted to do was, can we herd animals? And so we spoke to the farmer, and the farmer tried to draw the animals to us, basically started feeding them with hay. And then we then took SwagBot and we thought, okay, this is great. We'll move the robot now, and we'll try and see if we can herd them off to the right. And you can imagine animals don't know anything about robots. We don't even know whether they can hear high-pitched noises like the gears or anything like, there could be a whole bunch of things that we don't even know about. But as soon as we tried to herd them, they just ran off in all directions. So that wasn't going to work. So the classic, let's take a dog and herd animals, wasn't going to work in this scenario. This is the farmer laughing and giggling on the back of the ute, just realizing that we're just, there's no hope in the world around this scenario. But what we realized was, after we did a lot of work, but the animals eventually got used to the robot, not because of the robot, because the robot always was hanging around the farmer. And because the animals were used to the farmer, they started getting used to the robot. And then we realized that all we had to do was, instead of trying to push the animals, we just play a bit of Pied Piper process here. So they eventually got used to the animal, and we put a little hay stuff on the back of the bot. And now wherever the bot moved, the animals would follow. And that became a lot more interesting, and it showed that we could actually move the animals around. And that's important because of pasture quality. But what was more important was that we could start to measure the animals themselves as we were moving around. And so you ended up getting using laser data and vision data to detect individual animals. And the reason why this is important is because you wanted to measure the walking function of the animal, because if the walking function, the gait of the animal changed week after week, then it may indicate a health issue with the animal. Or if the animal was stationary for too long or sitting on the ground for too long, then that may indicate a health issue as well for the animal. So that became an important element. And in a lot of these grazing livestock farms, what you end up with is large areas. And so one of the key works that we looked at was energy conservation. So you take a terrain map, measure the contours of the terrain, and if you had to go from point A to point B, what was the most energy efficient path to follow to get from point A to point B, so that you maximized how much of the energy store you had. And some of the earlier work, we were getting up to about 15% improvement in the energy saving. And that was coupling probabilistic roadmap techniques with power modeling, along with optimization techniques as well. My last set of activity slides here is talking about the next generation of users. And when you look at robotics and applying it to farmers, you're dealing, if you remember from the beginning, 55 to 65-year-old growers, old age farmers, and they have a certain user interface that they want to deal with when it comes to robot. If you gave the same robot to a 21-year-old farmer, then all that user interface work and activity that you might have done on the robot, whatever, completely gets thrown out the window. And so there was a lot of interesting questions around what the next generation of farmers would look like. And we started to build different types of platforms for smaller holder farmers, especially the younger generation farmers. So this was one of the first ones where some smarts were in the wheel to look at control and motion. So this way you could kind of pull apart this robot, piece it together on farm, and off it went from there. And you could easily add different tools to it. So this was for a smallholder farmer work, where now what we started to look at was low cost platforms using a mobile phone on a selfie stick this time, because the mobile phone was a great power computer processor with camera on board. The selfie stick acted as a gimbal, and for these smallholder farmers, you actually got quite some good results out of that. And then we were fortunate enough to get some funding to go to Indonesia, Fiji, and Samoa. And you kind of look at it and you think, why would robotics want to be there? But the issue is that farmers all around the world are facing the same problems. So it's not so much that the robotics is the issue, it's more about, can you find the right model of engagement with those types of farmers? You know, how would they use the robot? How would you keep it sustainable in there? So there was a lot of activity in that space around the world, taking the robots to different parts of the world and looking at what you can do. And going back to the question before around transfer learning, can I learn crop growth in Australia and apply the same thing in Fiji? Or what can I do in terms of transfer learning to apply it in Fiji? So there was a lot of that happening as well in that scenario. And more recently, we did some work where we actually were teaching some kids about how to run these robots, and the same robots that they have on farm. And that really taught us a lot about the fact that you could train these kids who are used to PlayStations and Nintendos and whatever it might be within the space of half a day, how to use the robot. And if you gave them a 3D printer, then all of a sudden all these tools would get built. And that really kind of was the mechanism by which we thought you know, in Australia anyway, which is as big as the US or as big as Europe, you get this digital divide. You know, cities are where all the concentration of knowledge around AI, but also communication infrastructure, and nothing out in the region. So if you can start to build this sustainable network around a farmer, then you can introduce the robotic solutions in there. So that's it. I think my last slide is really about where, at least from a research perspective, where we're looking at this. As mentioned before, we spun out a company called Ageris, and this is our first platform which kind of takes on the previous work and puts it in there. But there's some interesting research areas that we're still trying to look at. And this is really, this one slide really kind of touches on it. I mentioned before about taking observations and then being able to predict forward ahead of time, coupling that with the biophysical models that you might have about plants and working with the agronomists around that, and how you might bring that together in whatever mechanism, whether it's machine learning or other formal methods, whatever it might be. How do you bring these things together to reduce the amount of uncertainty so you can predict forward ahead of time what's going to happen with the plant? So that's part of the research work that's still happening. And then what actions should you take? But also the coupling between the farmer and the platform, because at the end of the day, the farmer still has a lot of strategic knowledge, supply chain knowledge, weather knowledge, understanding what happened last year, what's happened in the paddock or the farmer next door. How do you couple that type of more abstract soft knowledge with the hard data knowledge that you get from a robot, and how does that get fused together so that you get this cooperative element that comes in, and from a research perspective? And the reason why is a farmer always engages with the farm and always engages with knowledge about the farm. So you're not trying to take the robot, going back to my first slide about a humanoid farmer, you're not really trying to replace the farmer. What you're really trying to do is bring the tools to the farmer, but then you have to make it easy for the farmer to engage with the bot and also co-learn, I guess maybe is the solution there with the farm. That's it. That's the end of the presentation. So thank you, but open for questions.
So thank you very much for the presentation. That was wonderful. Thank you. I'd like to ask you a question, if I might. You talked about the issue with the aging workforce on farms, and I know that's an issue in our country, and I suspect many other Western countries as well. Do you think that by making farming more technological and perhaps less physical labor, that might reverse that trend?
Yeah, that's the hypothesis, right? So that's the global hypothesis at the moment now. So, and we're just about to engage now with a TAFE college, a rural TAFE college, and so this is like a technical college out in the rural areas, which train those guys that, the guys and girls that work on farm that fixed tractors or equipment, and they're starting to look at smart farms, and they're starting to look at robotics on their farms to train those guys around what the future generation of those on-farm workers might look like. So, and what they have seen is as they introduce digital agriculture into their curricula, they're getting more high school students now going into those colleges to want to do something around ag. So they're seeing that trend happen because now ag is becoming a lot more exciting. Whether that continues on, it becomes is I think something that's still up in the air. But that's what the belief is at the moment.
Okay, thank you. Any other questions from the panel, Jim?
Sure. Yeah, maybe I'll start with a comment real quick. I love this concept you just proposed around integrating farmer knowledge and information into modeling. It's something I haven't seen or thought about, but very cool. So just one comment. And then a question around, you kind of triggered it with talking about this herding robot, which is cool to see. One of the big trends these days that I'm seeing a lot of good buzz about is regenerative farming, which couples things like cover crops and low or no-till operations, but also bringing livestock, like cattle or other animals back onto the farm. Do you see efforts in there? Like, do you see yourselves moving in that direction or trying to unify some of these efforts? Yeah,
so in Australia, so the old term for it, which they still use within the government circles, is mixed farming, and you're absolutely right. So they were looking at cover crops, what crops they might use to feed the animals as well as sell on the market, but then use the animals to kind of bring all that biosystem back together. Swagbot proved to be a bit more of a better bot for that as a platform because of the type of terrains in that type of environment. But we haven't, other than talking to farmers and speaking to them about what they're interested in, we haven't tackled it yet because it's quite complex. It's such a, I mean, just being able to sit down and go, what's the biophysical property of a lettuce in this certain soil type, and I'm just going to learn that now, takes a year of effort around that process, and to then come along and say, I've changed the quality of the soil because I've now planted this crop, and I'm going to throw in the animals and they're going to add certain types of nutrients into the process, becomes a lot more complex. It's coupling all the things that I've mentioned before, but how do you bring that together as a system? We haven't wrapped our heads around it yet, but you're absolutely right. There's a lot of that. There's a lot around that, and organic farming that also poses some more difficulty around machine learning and platforms. But it is we haven't tackled it yet properly.
Salah, could I get you to stop screen sharing, and then I'm going to go Chris, VJ, and Elizabeth with questions. And just for your information, the plural of lettuce is lettuces.
Okay,
that's what Google says.
Thank you,
Chris McCool. Over to you.
Salah, thanks a lot for the presentation. Sorry, let-I. No. Really interesting presentation. Look, you've worked with a range of different crops, and I was just wondering if you can give a bit of an insight. I mean, you've gone from orchards to vegetables as well as some arable farming type techniques. And you're looking at the different ways that farmers interact and do this process from start to finish. Was there a consistency there in terms of, in particular, is there a consistency in the low-hanging fruit where you can, have this low information that they have but get high return?
Yeah, so I think if we were talking about this the other day, thinking through it, is how there's a lot of work going on with how do you use robotic grasping around cluttered objects in an environment, the indoor office work and what it might be, and you kind of see the same trend happening here. If you can find distinct objects, so if objects are distinct, obviously that makes life a lot easier. So when you look at vegetables, dealing with say baby leaf, which is kind of like it's single but it grows and then it forms like a carpet over the bed. You can't do anything with that. Like it's just, there's no use. So distinct crops that stand up above the soil, because if you're worried about potatoes and beetroot, which are below the ground, there's only so much you can do with that. So distinct crops that stand above the soil and the vegetable crops, I think that's that kind of, it's easy to go back to Elizabeth's question. It's easy to do transfer learning, not just on the machine learning algorithms, but also in your knowledge and whatever, from one type of crop to another crop. So if you got lettuce, cabbage, broccoli, cauliflower, kale, that kind of level of activity. And when it comes to tree crops, there are certain, again, the distinct crops such as there's the special fruits like mangoes, avocados, apples, and plums, nectarines, etc. make life a lot easier as well. You can start to learn from one particular crop and transfer that crop. But when you start dealing with nuts, where they're everywhere, they're hidden, they're whatever it might be, it just becomes a lot harder. You can only do certain things around that space. So I think they're the kind of trends that we saw. Grazing livestock is just a much harder problem. It's animals and plants and soil and undulating terrain. It's really, from a research perspective, fascinating, but it's just a much harder problem when it comes to looking at getting the farmer engaged on that level.
Thanks a lot. Vijay.
Salah, again, just an awesome presentation, and just so many questions popping up in my mind. I wanted to ask two big picture questions, related questions about data-driven approaches. Clearly, that's central to agriculture as it is to so many domains. And data-driven approaches work if you can share data, you can build large data sets. So I'm just wondering, what's the future of kitty-like data sets for agriculture? At scale. My experience in the U.S. at least is that farmers are very, very protective about their data. They don't want to share it. And so that's one issue. The second issue is I'm always amazed at how we, in many fields, it's not a knock on robotics or agriculture, you go after data that's easy to acquire. But we almost never ask the question, gee, wouldn't it be great to get this data to answer this question? And so as you think about this ecosystem for bringing people together to solve this problem, what about novel sensors? Is there some, so for example, under the ground sensors, or sensing moisture at the surface level seems to be very superficial, and then sensing the volume also seems to be somewhat, that's the best we can do, I understand that, but are there opportunities for us to engage the sensor design and fabrication folks?
Yeah, definitely. There are two key areas that I think are still open that I've learned along the way that I would love to work with the physicists and the chemists around building novel sensors. One of them is root structure. Root structure of plants has such an important impact on plant health and on soil quality, and being able to measure root structure would be fundamental to knowing and being able to predict the future crop productivity. People have tried to start looking at, for example, ground penetrating radar and using different techniques to kind of measure the biomass that happens under the soil. So that's one, and that comes back to the days of mining where we tried to look at in-ground and above-ground modeling. So it was the same concept there. Can you model in-ground? Can you model above ground? So yes, superficial data up the top is easy to acquire, and it is superficial. It's what the farmers see. So being able to kind of provide them with that data engages the farmer before you can ask the question such as, I want to also build a sensor that looks at the root structure. But once you've done that, you've got this above ground, below ground kind of thing. And the other one is on-farm sampling of nutrient properties and micronutrients within the plant. So at the moment now, a farmer or an agronomist will come on the farm, pull off some leaves or some parts of the plant, put it in a bag, send it off to the lab. 2 weeks later, it comes back and it says, you should add X, Y, Z. The farmer's gone, I've just spent 2 weeks, there was a hailstorm, I've just thrown whatever it was, there's a whole bunch of things that happen in that to it. If you can build lab on a chip, which is really, I think, some of the things, so being able to do microfluidic devices that sit on a chip that you can put on bots that are able to sample, grind, fluidize, put it through, get the solution straight away, then that shortens that period. The whole thing that you're seeing with robotics now, if you think about ag, you're going from an undergraduate degree in ag science to researchers doing studies, to TAFEs and tech colleges trying to apply some of those studies to farms, to agronomists who know that knowledge, and that whole cycle is like somewhere between 5 to 10 years when some new knowledge happens here. And what you're seeing in robotics is the whole thing is just collapsing because you're starting to get the real-time agronomy, and the new sensors such as lab on a chip, below ground sensing would be some of the future things that I think were interesting. We worked with Raman spectroscopy recently, which was to fire a laser at a leaf and return and get the spectral responses back to try and detect microbes on plants. So salmonella, if you're going to tell salmonella, for example, or any type of food poisoning on farm before it goes through the processing, then you prevent risk of the sort of sensors like that people are working with as well. And that comes back to
I think we need to move on.
Right. Lots of data, but no big data yet in ag.
Okay, thank you. Elizabeth.
So thank you, Salah, again for the talk. And I think just to pick up a little bit on Vijay's comment, here I'm in England and we've got the same kinds of issues with sharing data, and we're doing some work collecting data other than the image data that is more typical, but it's definitely, I think, a direction to go in next. So Salah, I wanted to ask you a bit about, you spent a lot of time talking about the technical aspects, and one of the things that I think is a real barrier is looking at what are the sort of social and infrastructure barriers to taking what you've got in the field and actually looking for widespread deployment, on actual farms. And could you talk a little bit about the situation in Australia and the, what are you seeing there in terms of are farmers interested in what you're doing, or do they have the infrastructure to be able to deploy the robots? What do they think about, what are their workers going to say if, they get sacked because now we have a robot to pick the apples?
Yeah, well, starting backwards, Victoria, for example, one of the states has 26,000 less workers this year than it did last year because of COVID, and so the farmers are all up in the air about how they're going to get workers on farm. We have poor communication infrastructure in Australia, so going out to rural areas, don't expect 4G, 3G, 2G, whatever, in whatever form that you want. So a lot of the work that we had to do was about how do you do as much processing on the robot? So the robot collects data, but acts as a mobile server. It just sits on and it processes, and starting to look a little bit more at edge computing and what that might look like as well. So there's a bit of that. Social infrastructure, there's not enough people out there that can help farmers build robots, help farmers repair robots or anything like that. So there's a bit of education around what are ag robots, et cetera, and kind of, as I mentioned before, going through that STEM and TAFE elements so that you can build local communities in that space. So they're probably the key areas that we've been focusing on because of the lack of infrastructure. When we went to Indonesia, we had 5G connectivity everywhere, so it's just being able to deal with that kind of level of thinking. So they're the main things that we've been looking at.
Great, thank you.
So last question from the panel for Brian, and then we'll kick over to the questions that are on Slido. So for the wider audience, please put your questions onto Slido. Brian, over to you.
Hey, thanks, Salah, for the great talk. I'm wondering whether you can share some thoughts about, you have mentioned about there are several control variables in the farm. Is there any hope of doing some form of automated optimization of these control variables with inputs from the farmers themselves? Going forward, what else can be done here in this space?
Yeah, look, I think we introduced some of the work that we did with air traffic control. So we had done this work before with flight planning and air traffic control, where air traffic controller gets all this data and then they have to project where the plane should go next and control whatever it is. And what that is this decision variable from the human along with what comes back from the computing system. The farm is very complex because of the biophysical and because of the daily changes in weather patterns and whatever it might be. So it's one of those things where I don't think you can sit down, not yet anyway, and say, let's look at optimizing everything. And also farmers want still the final say because it's their business that they're running. So any decision support tools that you give or any optimization tools that you give, the answer usually is a collection of responses. It could be A, B, C, or D with certain, and you're letting the farmer then decide which one of those that they want to move with, because there's too many variables in there for you to make that call and not risk their business. So yes, you can bring in optimization. We're seeing it in irrigation systems, for example, where they do a lot of that. Coupling in the human knowledge is starting to get there, but it's still a very rich research area that's opened up. It'll probably only get applied to the big growers that that are looking for that 1-2% efficiency gains on their farm.
Right. Thank you.
Thanks, Salah. So I'm going to move over to some of the questions that have come through on Slido, and I'm going to focus on initially on the ones that are quite robotic-y. So the first one is, how do you determine the gripping point of a fruit based on the point cloud?
Oh, good question.
Change of gear.
Yeah. It's not just the gripping. Yeah, look, it's not just the fruit. It's the location of the branches and the leaves around the fruit. Because what really good farmers, they're really interested in you harvesting the fruit and not even scratching a bit of the branch, for example. So you've got it's a very complex problem when you're trying to look at all that. With the point cloud, we haven't sat down and just looked at a point cloud. You move obviously into the voxels, and then you move into whether or not you can segment them out as blobs and then use that information. And so that's the kind of cycle that we've gone through in there. But it's more complex than just identifying where the fruit is.
Okay, so you've got the problem of identifying the fruit, whereabouts on the fruit you should attach to it. And then I guess then there's the planning problem of how to get from where you are to the fruit and not interfere with other bits.
That's right, yeah. And different, like a farmer for plums will tell you, I want you to twist it before you kind of pull it off, because I don't want the stem, I need the stem to kind of, I want the stem to detach properly, because otherwise bacteria will come in at the point of that introduction. Other farmers will say, no, I want you to snip the stem on, so you got to go through that process as well.
Okay. Someone else has asked whether the automation can be applied in ways that sort of solve the economic and ecological problems rather than just about meeting the demand for production. So I guess does the technology enable a more sustainable mode of production, or is it just replacing humans with machines?
Yeah, the replacing humans with machines in agriculture. I mean, for all of us as roboticists, is one of the few areas where there's this conception in the public that that's what we're doing, but within the farming circles, there is no labor. It's very hard to come across labor all the time consistently. So it's not like we're sitting down saying we're going to get rid of all these workers and throw robots in there. Throwing the robots in there, one of the first things is around precision ag. So around the economic area, can I reduce chemical cost? Using robots that might be battery operated reduces all the oil costs and maintenance costs that you might have. Soil compaction, because they're smaller, so you get better soil aridity. So that happens as well. But everything around precision ag, so being able to kind of down to the individual plant, is meant to hit on the economic line. It's meant to reduce the costs, not just labor, but chemical costs, whatever it might be, and it's supposed to increase productivity of the plant.
Okay. There's another question which says that you talked about trellising as a way to structure the plant growths to make the automation problem easier. And as roboticists, that's often what we do, is we change the problem to make our life easier. Are there other things that could be done in the agricultural setting? The analog of trellising, but maybe for lettuce.
Yeah, I think, well, it's hard when you it's harder when you're dealing with how am I going to say this? So when it comes to vegetable crops, for example, it's harder to come along and say that there's anything that you can really change in the infrastructure. So normally what you see is this complete change in infrastructure, which is, for example, in Japan, I think they're growing 10,000 lettuces a day inside warehouses and whatever it might be, just on factory lines. So you completely change the infrastructure element to deal with that. But one of the areas that we've also looked at with some geneticists is whether, changing the crop, certain parts of the crop, if a crop becomes unhealthy, it gives off a certain spectral response. And if you can then attach a sensor that only picks up that spectral response, and you can identify whether there's a plant unhealthy or not straight away. And you see, people are starting to talk about whether or not they can change the genetic properties of certain crops to give off those spectral responses, to make it again easier for a robot to identify.
Okay, and there was another question about vertical. What are your thoughts about vertical farming, which probably follows on pretty directly from that.
It's a hot space. A lot of people are working on it. In Australia, there's been some studies on that. The amount of sunlight that we get, so the energy is always the biggest issue, right? So it's not about how many crops you can grow, what the uniformity is. It's about how much energy goes into that process. And at the moment now, in a place like Australia, the energy, just natural sunlight makes growing outdoors a lot significantly cheaper than doing it in vertical. But there's always going to be a place for that vertical farming here. And I guess in high density environments, there's a future for that. It's a much more controlled environment. makes life easier for robotics.
Yeah. So there's another question which is on what do you think is the role of open source robotics in the future of ag robotics? And I mean, it's maybe a sort of related question for Jim is what areas would benefit from shared development between the robot ag companies? So, take the first bit. So what do you think the role of open source is?
I think it's important because we have to remember that, I mean, food, well, I guess being a bit more philosophical here, food is part of nutrition security, part of national, and you're dealing with developing countries that have to, they have to still grow crops to feed their population. And so being able to do open source activities that allows those countries to actually help and develop tools and technologies that will benefit them is important. And the counter to that is we started initially with open source, but at the end of the day, if you want to deal with someone who's running a business, what they want is a solution that works, is reliable, maintainable, has a backing behind it in terms of being able to service and so forth. So there may be a reason for open source, but commercialization of the activity is also important. And then that kind of sometimes goes against the open source philosophy. So there's that balancing. I think both worlds would exist like they do in everything else.
Yeah. Jim, do you have a perspective on this? How those two worlds might play together?
Yeah, maybe a couple thoughts. I mean, certainly I think, open source things like ROS, for example, have been great foundational pieces that get leveraged not just in agriculture, but across the board in robotics. I think, so you mentioned earlier data and kind of how do we share data? How do we get data sets that can be leveraged across agricultural domains? I don't think we figured that out, but I think there's a really big opportunity there in trying to find standardized data sets. I think we've had there's been less opportunities that I've seen for specific applications where you would open source things. I do think though, you pointed out these different indices. So a lot of the research literature around multispectral or hyperspectral indices around plant health and things like that, getting that information out there has been really valuable too. It's not truly open source in terms of code, but just kind of that shared information base has been really valuable for us.
Okay, thank you. Somebody asked a question about the cost of errors. The new robot messes up and bankrupts the small farmer in one season. You just need insurance, right?
That's right. There's probably and protection from a shotgun as well. So, but yes. Look, it's always on our mind, and all the farmers will tell you the same thing too. What happens when the bot goes rogue and it starts to cut across the beds and rip out my plants and all that stuff? And some growers are happy. They're big enough to give you some slice of their paddock and say go for it. But we've got to get to that point where it's really robust enough to be able to use with the small farmers as well.
Okay. A somewhat related question is how enamored are farmers about owning robots that will be working on their farms? Are they really happy? They see it as a necessary evil?
My experience is, it's exactly right. The early adopters, the big guys right at the beginning, they know where the future is, and so bringing that on is what they're looking for. Whether they own it or lease it, or you come in as a service, etc. I think those things are still up in the air. A lot of farmers still like kicking the tires and owning their own assets and whatever it might be. So that's, they want to buy a bot, but there is room there to understand whether or not there are different other models of engagement. Then you've got the next guys who can see that they need to improve by 10, 15%, and they're waiting for those first guys to kind of use the robotics, and they come on board, right? So the classic, whether mum and dad who own a 5-hectare plot will one day have a future robot. I think that will happen. It's just probably a while away before it does happen.
Okay. Another question is related to fixed sensors in the environment. Could you see robots installing fixed sensors, perhaps to measure soil moisture or chemistry? And how do fixed sensors and robots interact? I think, in an efficient way.
Yeah, it definitely, we shouldn't be ignoring the fact that actually what we're trying to do is build a digital ecosystem. So soil sensors, even plants, like, for example, putting sensors on tree branches that can measure water flow or measure light interception, for example. And how does a robot that might be going up and down rows talk to those sensors? And you start to build up an ecosystem of that digital knowledge, and that I think is something that is definite. It's a question of when do you want to sense and act simultaneously and quickly on something, and that's where I think the robotics will kick in. At the moment now, the robots are becoming these ubiquitous tools that, you know, hold all these things together, but I don't think that's probably the future. The robots will get smarter, simpler, lighter, and talk to other sensors that are already embedded in the ecosystem.
Okay, thank you. Panelists, do you have any last questions for Salah before we wrap up? Chris.
I don't know if it's that quick a question, but you talk about individual plant action or interaction. Where do you see the limit of this? Like, what's the final end goal with being able to do all of this individual plant action or interaction?
I don't see the limit technically. I see the limit more about whether or not it makes sense economically for the farmer. I think that's, you know, so it could be that all we're doing is reducing the resolution, or sorry, increasing the resolution of what we're doing. So instead of on a paddock, it might be down to a row or half a row. But I think they're questions that once you can start to do something really elaborate, then it's an economic question. So more then it becomes to the farmer whether or not that's something that they should implement, because I think there'll be economic questions which we don't know yet. Well, I don't know yet about how whether doing per plant is the right thing or not. Per plant knowledge might be interesting. Per plant spraying, not too sure.
All right. Any more quick questions from the panel? If not, then we might wrap it up. Please, again, join me in thanking Salah for a wonderful presentation, brilliant questions, and fantastic discussion. Thank you very much.
Thanks, guys.
Good morning.
Questions too.